Welcome to this explainer. Today we are diving into a really fascinating intersection of biology and technology. We're looking at how mimicking the biological human brain might just save the world's data centers from a massive impending energy crisis. Think about it. Every single time you generate an image on your phone or ask a chatbot to draft an email for you, there's a huge, hidden physical energy cost happening in a server farm miles away. And as millions of us use these tools every single day, we're fast approaching a critical moment for artificial intelligence. The secret to how neural networks save energy, though, well, it might literally be sitting right inside our own heads.
Just to wrap our minds around the sheer scale of this problem, consider this. Training modern AI models like GPT-3 emits as much carbon as several transatlantic flights. That is a staggering environmental cost for just one piece of software. But here's the wild part. New brain-inspired or neuromorphic chips are promising an unbelievable 1,000x reduction in energy consumption. We aren't just talking about a tiny 10 or 20% upgrade here. This is a complete paradigm shift in how computers run. Imagine taking the electricity needed to light up an entire massive stadium and shrinking it down to power just a single light bulb. That is the kind of scale we're talking about.
So, let's dive into this existential threat and ask the million-dollar question. Can a chip mimicking the human brain actually save our data centers from this energy crisis? We really need to know if biological engineering concepts can scale fast enough to meet AI's relentless exponential power demands. And I do mean exponential. The foundational models powering these systems are doubling in size and complexity every few months. The hardware simply has to catch up before our electrical grids are just pushed completely past their limits.
To understand the fix, we kind of have to look at how computers have been built for decades, because there's a massive structural inefficiency going on. On one side, you have the traditional von Neumann architecture, which totally separates the memory, where data is stored, from the processing unit, where the actual math gets done. On the other side, neuromorphic architecture co-locates them. It puts storage and computation in the exact same physical place. Now, why does that even matter? Because physically moving electrons across a motherboard from a memory chip to a processor takes significantly more energy than doing the calculation itself. By putting them together, energy use just drops off a cliff. We actually call this structural inefficiency the von Neumann bottleneck. Think of it like a truly terrible daily commute. Imagine a worker who has to drive miles down a congested highway just to retrieve a single file from a filing cabinet, bring it back to their desk, do a tiny bit of work, and then drive all the way back to put it away. And they do this over and over and over again. It wastes an incredible amount of energy. Plus, this constant commute generates immense heat, meaning data centers need massive, power-hungry cooling systems just to keep the servers from melting down. Neuromorphic chips, on the other hand, give that worker a highly efficient home office. Everything they need is right there on the desk. So the key to totally ditching that commute lies in spiking neural networks, or SNNs for short. They pull off this unprecedented efficiency by acting exactly like the biological neurons in your brain. Instead of processing the dense, continuous, heavy streams of data you see in standard AI, SNNs use sparse, binary spike trains. In plain English, they communicate using tiny, sudden zaps of electricity, literally just a 1 or a 0, and they only do it when absolutely necessary. They wait in total silence and only compute when a highly specific event triggers them. It makes them incredibly lean. Because SNNs are event-driven, they follow this beautiful, really simple biological rhythm. They accumulate electrical voltage from an input, wait patiently until that voltage crosses a specific activation threshold, and only then do they fire a spike. That means they sit perfectly quiet and consume zero power until that spike actually happens. Compare that to standard computer processors. Standard chips are forced to march to the beat of a global clock network. That clock acts like a relentless, high-speed metronome, forcing the whole chip to draw power on every single tick, even if a section of the chip is sitting completely idle. SNNs just bypass that exhausting metronome entirely. When you map out the differing energy profiles between standard deep neural networks and spiking neural networks across the basic components of hardware inference, the entire shape of the energy consumption transforms. Traditional deep learning forms this incredibly wide footprint, drawing massive power just moving memory and crunching huge numbers. But when we switch to brain-inspired models, that energy footprint shrinks radically inward. We're essentially trading brute force calculation for highly efficient event-driven pulses, and that completely alters the power demands of the hardware.
Let's quickly run through those 7 components of inference energy: compute, memory, state, temporal, activation, leakage, and clock.
Now, while SNNs drastically reduce the compute, activation, and clock energy, it isn't exactly a free lunch. They do introduce some mandatory new overheads. Specifically, they need energy to maintain the internal state of the neuron, meaning its membrane potential. Basically, the artificial neuron has to spend a tiny bit of continuous juice just to remember how close it is to firing. There are also temporal processing penalties, because SNNs evaluate data over multiple discrete time steps, just like a real brain processing the passage of time.
But here's the crucial point. Despite those new biological overheads, the overall compute savings are absolutely massive. Why? Because SNNs replace power-hungry multiplication, which is known as multiply-accumulate operations in standard AI, with simple accumulate-only addition. This is a game changer because for a computer, multiplication is much harder than addition. It requires vastly more physical logic gates and microscopic transistors firing all at once. By skipping that complex multiplication stage and just adding pulses together, we slash the operation energy by roughly 5 times. It is a major breakthrough in how networks save energy at the most basic arithmetic level. Now, to actually build these networks in physical hardware without running right back into those terrible off-chip memory bottlenecks, engineers are turning to some incredible new components called memristors. Imagine a grid of microscopic wires arranged in a crossbar array. At every single point where 2 wires intersect, you have a memristor. These intersections act exactly like artificial synapses. They store the weight or the memory of a connection simply through their physical electrical resistance, and they do it without needing constant power. This lets us actually perform the computation directly inside the memory itself.
When it comes to learning on the chip, the process is incredibly slick. We can train these memristors directly on the silicon using very precise voltage pulses to tweak their conductance. We just send a pulse in, measure the resistance locally, and update it right on the spot. By adjusting that physical resistance right at the intersection of those microscopic wires, we entirely eliminate the massive energy drain of sending data back and forth to a distant cloud server. All the learning and the memory updates happen right there, locally on the chip.
And hey, the innovation doesn't stop with electronics. Beyond electrical memristors, researchers are actually building neuromorphic systems using silicon photonics. That means computing with light instead of electricity. It sounds like sci-fi, but think of it like a glass prism separating white light into a rainbow. Using this exact principle, we can use distinct colors of light, specifically lasers, to process multiple independent streams of data at the exact same time through a single channel. Because the physics here is totally analog, these photonic neural networks could potentially be 10,000 times faster than the best electronic processors we have today.
Putting these technologies head-to-head, the real-world efficiency gains are just staggering. While traditional GPU-based AI sits at this massive baseline of 100x energy consumption, early neuromorphic chips drop that to just 1 to 3x, mostly thanks to that event-driven design. But looking further into the future, a spin memristor prototype could drop that relative energy consumption down to a tiny fraction of a single % compared to standard GPUs. By perfectly mimicking the ultra-low power nature of the human brain, the efficiency gets almost unbelievable. Let's put a hard number on this. By combining these hybrid spiking architectures with sub-threshold analog designs, custom accelerators are hitting some extreme physical efficiencies. We are talking about consuming a mere 0.42 picojoules per electrical spike. To put that abstract number into perspective for you, a single picojoule is 1/trillionth of a joule, literally a ghost-like whisper of electricity. It's an unbelievably minuscule amount of power, proving that these theories are actually yielding spectacular, real-world results in the lab. Anchoring back to that 1000x energy savings we talked about at the start, this specialized hardware directly enables a booming field called intelligent edge computing. We're talking about revolutionizing things like smart city traffic analysis, untethering autonomous robots, shrinking down embedded biomedical sensors, and powering remote IoT networks way out in the wilderness. These devices can now learn, adapt, and react locally, in real time, without draining their batteries or needing to phone home to a giant power-hungry cloud data center to do their heavy lifting. The implications here are absolutely thrilling. So as we push the absolute physical limits of artificial intelligence, I want to leave you with one final thought. Will brain-inspired neuromorphic chips unlock a truly sustainable future for AI, or are we just delaying an inevitable power crisis? The hardware is already here, and the staggering efficiency is proven, but scaling it up and getting it out into the world to meet our soaring demands, well, that is the next great frontier. Thank you so much for joining me in this explainer. Keep asking questions, stay curious, and keep learning.